Hi, my name is Michael Spedding. I've been a pharmacologist now for, 52 years since my first experiment. I've been on research committees in top pharma for 35 years, seeing every way drugs can pass or fail. And I've set up 2 research centers, 11 drugs into the clinic from my groups. And what is more, we've got 10 years of Spedding Research Solutions, my own little company, and the first drug into ALS in phase 2. So that's given me an awful lot of experience. And what I'd like today is to actually show you something quite quickly, which is some ideas that I have that we're doing things in a suboptimal way for drug discovery and indeed for experimentation. These are my views, they're not EUFAR's, and I'd just like to sort of have a relatively hard-hitting, slightly humorous look at how we can improve and how I can go against some of the established tenets which you might otherwise see. So I'll share the screen. So effectively now, I believe that actually over-reliance on Gaussian distribution concepts, lack of philosophy, particularly Popperian philosophy and a Bayesian approach, are a major impediment to drug discovery. What I look for is something that's quite exceptional. We can find things which are quite exceptional. We've got to do it a different way. Look for black swans. So these are my views. And I also believe the reproducibility crisis is being addressed in the wrong way. So you'll see what I think about this, because these are some books that I've appreciated through my life or recently. And I think they're quite important. Spiegel-Halter's books about statistics are great. And his Bayesian, nice, simple Bayesian approach for everybody there. Karl Popper is fundamental to my philosophical thinking. And The Black Swan by Taleb is really an important book. You may not believe everything within it, but it means that there are major catastrophes or even possibilities of great things which can happen unexpectedly. And that's because we overindulge in the Gaussian curve and regressing to the mean. And we actually leave, therefore, in the outliers, what can be of great therapeutic benefit, squashed by more numbers. And for this, I've got to go back because it's only now that I'm beginning to realize that I've spent all my life doing things slightly differently from most other people. That's because I had some tremendous PhD supervisors. One was Max Wheatman, always do the experiments. They don't work the same as in their papers. They're not reproducible. So that was inherent to my start. And it says that's the way science progresses. And my external PhD supervisor, Roy Britton, was the first pharmacology director at Glaxo. And he discovered drugs worth £650 billion in cumulative sales, when we knew very little of what we know today. So why is that? Well, one of the reasons is because we've learned more and more, but as we go on, we increase the number of variables. And so actually you control drugs not very much more than you do with good pharmacology. And so I also believe you must have a philosophy. And I didn't get very good A-levels. How could I be so pretentious to discover the secret of science? Well, Karl Popper, who you must read, just read the wiki page, because actually it's quite good, says you can't. You can disprove hypotheses with good experiments. So I can live with the idea of being less wrong than others. And his definition of science is what's experimentally tested and falsified. And also, he pointed out that all swans are white until you find a black one. And this is the danger of a too much reliance on Gaussian approach. If you believe in Popper philosophy, total confirmation does not exist. It's the limits of falsifiability which you need to be able to see how far you can trust your hypothesis in experimental conditions. And that means more exploratory work to define the variables which are going on. And therefore, I push the bar towards exploratory being more important to confirmatory, because confirmation is not existing. You're just doing it on a bigger scale. And you need, obviously, but at the same time, you've got to have all the good experimental practice, which you can have. And the Bayesian approach works on evolving probabilities. The initial odds before you start the experimental probability working times a likelihood ratio and final odds. And actually, I trained my brain when I was about 22 to think in probabilities. And it's inherent to the way I do things. So why is drug discovery being so difficult? Well, man is different. We've evolved to run and to have a long life and have a really remarkable metabolism. and you can see this in the evolution video. Disease biology is extremely complex. You can see why in the aging video. And we underestimate massively human de novo mutations and also in life mutations. And that's a thing I'd just like to take up a little bit more, because this is just a number of mutations in the endosomes, lysosomes, affecting autophagy in a disease which is, a lot of people have got it, hereditary neuropathies. And you can see there are so many of them, it's almost impossible to target. So therefore, you've got to go on the downstream effect of autophagy as an emerging common pathway mechanism, which you can then test and modify. That's one way of doing it anyway. And one of the points is there are about 300 billion nucleotides in the human genome, but there are 8 billion people now, each with 70 or more de novo mutations. So the human race is experimenting with almost all non-lethal mutations, showing that rare diseases are central. And therefore, people, when you regress to the mean in large clinical trials, you're ignoring people with very specific needs. And in the reverse effect, this is the most obscene effect. Kathleen Folbig spent 20 years in prison because she had a mutation in calmodulin, and her 4 children died, which some specialists said was statistically almost impossible. And she was sent to prison for the children dying of calmodulopathies. So, and there, it's the mean and the Gaussian approach is not appropriate. I'm not saying it's always wrong. We're in very good defined conditions, such as gambling, etc. It is, but where you've got a lot of variables, you've got to be very careful. And these are the variables that you find in pharmacological conditions of a receptor interaction. I made a list of them in 2011. I'm going to show you these. It's just you've got an awful lot of them. And that means that the experimental conditions are going to play an enormous part. And it also means that this is the reason why Roy Britton's group was so successful 50 years ago, because they had, first of all, a receptor idea, and then they selected the compound in the pathological condition. That is at 50%, and using pharmacology to eliminate the variables. And so this means that all of these things which can change in a pathological condition are taken into account. And so we lost a lot of ways by just using very reconstituted systems and selecting in those when we should have been, as I've always tried to do, select in the pathophysiological situation. So this gives a few experiments which I've always tried to use to control a black box, which is well the black swan, which you're actually doing your experiment in, because you can have a black box, which is either a cell, organ, or body. You put the experiment in and you see what comes out the other side. But you don't really control what's going in here. And I can tell you 50 years ago, we didn't even know what was going on at all. But then if you do the experiment, you should also do that. But if you then go ahead and run with that, you may well be wrong. What I've always tried to do is to find a way of running the experiment in reverse through the black box. So therefore, you can actually see what comes out the other end in the opposite direction. It gives you a bit more confirmation that it's not just an artifact, which is giving you the result that you've got. It's not very simply. I had some drug, I had a set, actually this worked twice, 2 sets of drugs, which would either inhibit contraction or relaxation, but not the others. And that made me think, well, this is different. And subsequently, they found a completely different, working in a completely different way, while it was being previously classed together. So the classical way going ahead is you do an exploratory definition of variables, and you can't even publish these definition of these variables if it's n equals 3 in BJP, which I think is wrong. It should be allowed in supplementary material. Then you do a very large experiment in a rigorously tightly controlled, very large N. You need to have the rigorous tightly controlled, right? But I think you're not testing the hypothesis very much at all. So when you take it somewhere else, it's not going to work. That's one of the areas where reproducibility is difficult. So what I've always tried to do is multiple experiments, sometimes with smaller n, but the extremes of the hypothesis with very clear effects. So if you can't get clear effects, your variables are too much, or your drug's not working the right way, and taking into account experimental control variability. So you do a lot of exploratory definition of variables. For example, I can even do n equals 1 of a concentration response curve to magnesium in the medium. You don't expect it to change, but it's worthwhile knowing. And then you do different experiments at the very limits of where you think the hypothesis can hang. And that gives you 3 different experiments, or in my case, quite frequently what happens is actually it's 3 or 4 different papers in professional journals. There's a big review of what they mean. And this means that, say, ATP or adenosine receptors being different, different calcium channel modulators working in different ways, actually it becomes so obvious after that, it's very quickly common knowledge rather than spreading this. So I think it's a very important aspect. You also got to take, obviously, into account molecular causes of diseases, evolution of humans, and why not use all the expert knowledge which was curated with 35 years of NCAU from. So I just like to say, your experiments now, you should think about how they're going to look in 50 years. Obviously, I won't be here, but if you go back 50 years to what I was doing, my very first set of experiments at PhD, I had a fantastic PhD supervisor, Roy Britton, and also we were in an area whereby it was very controversial. Jeff Bernstock had just produced the purinergic nerve hypothesis, which was the hottest topic in pharmacology in the 70s. And we found the very first antagonist of ATP. It wasn't a very good one, 2,2-pyridine cytogen. And we also found that it differentiated adenosine and ATP receptors. That was, I presented that to BPS in 1974. And Jim Black and John Vane on the very front row were very excited about it. Said, "Whoa, you can separate ATP and adenosine receptors with that. That's really interesting." Of course, now it's so obvious, nobody thinks it's of any interest at all. But at the time, it was novel. And actually, that was also introduced me to nomenclature, because Jeff then virtually redid our experiments about 45 years later and called them P2X or P2Y, P2, and or P1 and P2 time. Therefore, when you do a literature search, you go back to start at P1 and P2 and you quote Jeff rather than our paper before. But that gave me a clue about how important nomenclature was. And if you go back, we also had difficulties about reproducibility because we sent this compound around the world. Some people said, "This is great, this absolutely works." Other people said, "Oh, it didn't do anything against my ATP responses." And so we actually had to write about a paper about the reproducibility of 2,2-pyridine cytogen. And actually, I always keep projects in my back pocket for the future. You wait for the wheel to turn around for technology, and we were able to screen it on the site of action, which was the P2Y1 receptor, which is selected for 25 years later in conjunction with Jeff. And so having said that, though, I did leave the field, and past 50 years I've been particularly successful for P2 receptors, antiplatelet drugs. And now we're coming back to find some areas for it. Making the right choices about where your knowledge can carry you is probably worthwhile. Also notice that Jeff was far too enthusiastic about ascribing receptor number to anything that resembled a P2 receptor in structure. And the NC committee had to really do some pruning. So that's be humble. Think what it looked like in 50 years' time. But you can go and get black swans, that is, very different compounds, by going and looking for them specifically in pathophysiological situations. And I'm not going to go into this. I just want to point out that you can do it. We therefore looked at a series of risperidone analogs with a brain vector, and we screened them phenotypically on something which was really crucial, the hippocampus, the prefrontal circuit, which we'd established some 30 years ago as being a really interesting thing for psychiatric diseases. And now it's the main issue, it's been validated elsewhere. If you go into the psychopharmacology video, you can see why. But therefore, we actually screened for that, as going, look, saying that if black swans exist, we want to find one, and we're going to do it with our best available shot. And we actually screened phenotypically on these systems a whole series of compounds. And we still don't know why this one was so good. The receptor profile doesn't really explain it. And it had amazing effects on hippocampus prefrontal cortex, includes stratum lacunosusum, very specifically. Enhanced hippocampal prefrontal coherence, It fully blocked the effects of phencyclidine and ketamine on EEG, and you could actually restore social behavior in rats on phencyclidine. It inhibited the inhibition of long-term potentiation in the hippocampal frontal cortex and blocked bioptopsin stress, and fully restored a unique electrophysiological profile. And so that means you can actually go look for a black swan deliberately. We still don't know really how it worked. It was possibly a combination of receptors, possibly something else. But we hope that in 50 years' time, somebody will revive it. Actually, we couldn't get rid of the alpha-1 effects, and therefore it did cause postural hypertension, which many antipsychotics do, but the company was looking for a whiter than white swan at the time. And we should have gone directly straight into schizophrenic patient volunteers, because there's now getting to be good evidence that alpha-1 receptors are actually slightly different in schizophrenics. And that would have been a marvelous compound to go through. I'm still extremely proud of it as an example of looking for a black swan and finding one. I just did a little advertisement for metabolomics. It's a massive future. In the next 50 years, glycosphingolipids with all their complex sugars and lipids are going to take center stage. And this is something we've been working on for the last 10 years. Our ALS drug works on it. And I think that in the future, lipids and sugars are infinitely more complex than just nucleotides, and will actually come to be recognized as really great therapeutic targets. Proof of concept is an experiment, and experimental design is critical. Look at the data. And I actually seriously think that with small changes and a more adventurous and pathophysiological approach, we'll be able to look at some of the big diseases of our time in a different way. For aging, see the aging presentation. Okay, thanks. And I'm at the conference, and you can then argue with me at any point of time unless I'm running somewhere. Okay, take care. Cheers, and thanks very much.